Let's study hydrostatic equilibrium. If you go out to the ocean, many times at the ocean you can observe a log that is floating very happily on the surface of the ocean because it is of a less density than the water around it, because therefore the water pushes up on it and it becomes buoyant. But some of these logs, they get what's called waterlogged. They get full of water, so they sink down to a certain depth and they float at that certain depth. They're quite happy to be there, not all the way in the bottom, not all the way in the top, and they are submerged waterlogged logs that just are floating at a certain depth beneath the surface of the water. Therefore, they're in some kind of equilibrium. They're not going up and they're not going down. So there must be a balance of forces between them. Now, the log has a certain mass, m, so therefore it has a certain gravitational force pulling it down, mg. So why doesn't it fall down? Is because that there is a pressure differential force pushing it up. For example, the water has a certain pressure, and as you know, as you go down to the bottom of the swimming pool, then the water gets deeper, the pressure gets higher. That's because if you examine 1 cubic foot of water down at the bottom of the pool, it is holding up a huge column of water on top of it. This column of water is pressing down on that lower 1 cubic foot, and if you press down on something, then you increase the pressure by which it presses back. Now, if you look at a cubic foot of water about halfway up, it is only supporting about a pool full of column of water, so therefore it only needs to be compressed to about half the pressure at the bottom. Indeed, as you go down into the depths of water, the pressure increases with the depth that you go down. The deeper you go down twice as deep, you get twice the pressure. And of course, water pressure presses in all directions. It's indifferent to the direction that it presses in. That means at the bottom of the log, the water at the bottom of the log is pushing up with a pressure that is determined by the depth of the bottom of the log. And the water at the top of the log is pushing down with a depth that's determined by the top of the log. Now, there is less pressure at the top of the log than at the bottom of the log inside the water, because the top of the log is not as deep as the bottom of the log. Therefore, there is more pressure pushing up than there is down. Therefore, there's a balance between the pressure differential, between the pressure at the bottom of the log, the pressure at the top of the log, and the gravity pulling down, so the log just sits there. Now, suppose that a octopus comes by and just sits on the log. That's going to increase its mass. Therefore, the log is going to now have a dominant force pulling it down. It's now going to go down. But as it goes down to a lower depth, with the octopus sitting right on top, then the pressure increases. So the differential in the pressure between the top and the bottom gets stronger the farther it goes down. So it just finds a new equilibrium position where the pressure differential between the top and the bottom is now equal to the weight of the log plus octopus. So this submerged log can go to various different depths, and it achieves an equilibrium called a hydrostatic equilibrium that is the balance of gravity pulling that object down and the pressure differential inside the fluid pushing it back up. Now, if we just take the log away and we go to the water itself, we can imagine a layer of water in here, and now this is just a layer of water. And the layer of water has a certain mass. So that layer of water might want to sink to the bottom. But the water beneath it is pressing up with a certain pressure, P lower, and the water above it is pressing down with a certain pressure, P upper. Now, P lower is greater than P upper. So this layer of water is supported in place by the pressure differential of water pushing up below it being greater than the pressure of the water pushing up, which balances its gravitational force pulling down. So this layer of water just sits there. Now, if we go to inside a star, then the star has self-gravity. So as you go into its center, then the pressure increases. because of the self-gravity pulling in on the particles, compressing it. So the greatest compression and density is at the middle, therefore the greatest pressure is at the middle, and as you go outwards, the pressure lessens until it is only much, much less at the surface. So if we examine any layer of material at some interior point, a shell at some interior point on the star, then this shell that we're examining has a certain mass. So therefore, it will be pulled into the star because of its mass. So the mass interior to it in the star is pulling it in, trying to make it be all the way to the center, because mass attracts mass, so the mass interior to this shell inside the star is trying to contract it down to a point. But because there's a pressure differential in the star, then there is a pressure here pushing out, and there's also a pressure up here pushing in, because pressure pushes in all directions. Now, because the pressure increases as you go into its center, then the pressure pushing out is greater than the pressure pushing in. So this layer will sink until it achieves just such a balance that the gravitational force, mg, pulling it in, is equal to the pressure differential on the pressure pushing out at the bottom being greater than the pressure pushing in at the top. And therefore this shell stays in place, and the next shell stays in place, and the shell inside stays in place. And all the stars, all the shells in the star stay just where they are because each one is in hydrostatic equilibrium. That is, the force of gravity pulling that shell to the center of the star is exactly equal to the difference in pressure pushing it out.